In this second part of the long-run production material, I'm going to look at the cost minimizing input choice or input bundle. The idea here is that firms try to select inputs to produce a given output level at minimum cost. So once again, the idea here is that firms are trying to minimize the cost of producing a given level of output. And we're going to assume that the output that the firms are trying to produce is going to be the profit maximizing output. So before we get into that in much detail, I just want to review a little bit about the cost. So the firm's cost can be given by this equation. So the firm's total cost is going to be the wage W times the number of workers hired plus R, the price of capital, times the units of capital hired. An ISO cost line then will illustrate this concept of cost for us. The ISO cost line is going to show us all combinations of inputs that the firm can hire for a given cost. So let me put up a line here for a particular ISO cost line. This ISO cost line again is showing us all combinations of capital and labor that the firm can employ for a given cost. So maybe this ISO cost line is showing all combinations of labor and capital that will cost the firm a total of $1,000. Here's another ISO cost line. This might be showing all combinations of labor and capital that can be employed for maybe $400. So we can think about these ISO cost lines in this manner. Also, just a brief review, the vertical intercept is the C divided by R, and the horizontal intercept is C divided by the wage. Okay, so let's look at this cost minimizing input bundle with a diagram. So the goal of the firm is to get on the lowest possible ISO cost line for a given output level. So if the firm wants to produce 100 units of output as its profit maximizing output level, the best way to do that is to get on the lowest possible ISO cost line. And this is going to be a picture of a firm hiring the optimal input mix, K star and L star. Okay? There are other ISO cost lines that the firm can get on to produce 100 units of output, but those are going to come at a much higher cost. There's an ISO cost line, for example, I'll just dot it in here. Here's another ISO cost line. We can get on the isoquant here and still produce 100 units of output, but the point is higher ISO cost lines are associated with higher costs. So we could produce this output at a lower cost, getting on the lowest possible ISO cost line. Now what's going on here at this point? Star. The marginal rate of technical substitution, okay, is equal to the ratio of the input prices, the wage divided by the price of capital. And we learned that the marginal rate of technical substitution is the marginal product of labor divided by the marginal product of capital. So we can write it like this. So just a step back again, all I'm doing here is that the slope of the isoquant is equal to the slope of the ISO cost line in equilibrium. The absolute value of the slope of the isoquant is the marginal rate of technical substitution. The absolute value of the slope of the ISO cost line, as we showed before, is the wage divided by the price of capital. So geometrically, the slope of the ISO cost line and the slope of the isoquant are identical when we are choosing the optimal input mix. Now all I'm saying is that the marginal rate of technical substitution, as we showed before, is the marginal product of labor divided by the marginal product of capital. If we were to take this condition and solve it, or rearrange it, I should say, we'd come up with an important expression like this. In other words, when we're hiring the optimal input mix, we want to be hiring inputs in such a manner that the marginal product of labor divided by the wage rate equals the marginal product of capital divided by the price of capital. The left-hand side is the additional output that results from spending an additional dollar on labor. So the left-hand side of this equation tells us the additional output that is obtained from spending an additional dollar on labor. It's a bang for the buck measurement. How much will our output rise if we spend one more dollar on hiring workers? The right-hand side is a similar idea. This is going to be the additional output that results from spending an additional dollar on capital. If we were to spend just one more dollar on capital, how much more output would we get? This is another bang for the buck measurement. If we're spending our money wisely in producing a given output level, this condition must be true. In other words, there's not going to be an advantage of spending one less dollar on labor and one more dollar on capital, okay? And we're going to see our output go up. That's not going to be possible when we are choosing the optimal input mix. So this condition must hold. There's no way to rearrange our spending to get more output for our money. All right, let me get a clean sheet up. And let's do a utility maximize, or not a utility maximizing, is very similar to that. Let's do a problem finding the optimal input mix. Let's set up the problem as follows. So let's say a firm has the following production function. The firm wants to produce 16 units of output. That is its profit maximizing output level. The firm pays workers, each worker, $100 over this time period, and capital will also be $100. We want to find the optimal input mix. How many workers should the firm hire? How many units of capital should the firm employ to produce this 16 units of output at the lowest possible cost? So what we need to get is the marginal product of labor. And the marginal product of labor will be given by the following. It's a partial derivative of the production function with respect to labor. So I bring down the 1/3 in front, and then 1/3 minus 1 is why we have minus 2/3 over there. And then the marginal product of capital, again, is a partial derivative concept, taking the partial derivative of this. We get this result. So the next thing I'm going to set up is our equilibrium condition. And now we're just going to plug in what we know. The marginal product of labor divided by 100 equals the marginal product of capital divided by 100. Oops, capital. Okay, sorry. Now we want to simplify this by solving it either for L or K. So a few things to note. The hundreds are on both sides, so they're going to cancel if we're to multiply everything through by 100. We got a 1/3 here and a 1/3 here. That is going to just cancel. So rewriting. We're left with this expression. And now we just want to simplify this, again solving for L or K. So using the rules of exponents on the left-hand side there, likewise on the right-hand side. And now we're just going to multiply through by the two terms in the denominator. So if we multiply everything through by L to the 2/3 power and everything through by K to the 2/3 power, I'll go over here, we'll be left with this. Using the rules of exponents, we get K equals L. So when the firm is producing its 16 units of output at the lowest possible cost, it's going to hire an equal amounts of labor and capital. Okay, so here's our next step. The next step is to plug this result back into our production function. Okay, but before we do that, we want to set our production function equal to 16. That, after all, is how much output we want to produce. This could have been any level. I'm just pulling 16 out of the hat here. So we're assuming that the firm wants to produce 16 units of output. Presumably it's its profit maximizing output. So setting the production function equal to 16, okay, and now we're just going to substitute this result into the production function. So where I see a K, since K equals L, I'm going to just plug in L instead. So we get 16 equals L to the 2/3 power. We want to solve for L, so I'm going to raise both sides to the 3/2 power. So we get L equals 16 to the 3/2 power, and solving this, L is just 64. Okay, and since K equals L, K equals 64. That is our optimal input mix.